Okay, so in the previous example, what we saw was if I have a graph corresponding to the function y is equal to x squared, or in other words, f of the function fx is equal to x squared, then I could look at 2 points, P and Q, and try to estimate the gradient of the tangent at point P using the gradient of the secant PQ. So the gradient of the secant PQ looks like this. The gradient of the tangent at point P is here. So what we saw before was the closer and the closer this point Q gets to point P, then the closer these two gradients are going to match. So the gradient of PQ is going to get really close to the gradient of this tangent at point P. So let's say this point P is located at x is equal to c. Let's say this point Q is located at x is equal to x. Okay, so obviously if the x value at point P is c, then that means that the y value is f of c, and if the point Q is located at x is equal to x, then its y value is going to be f of x. Okay, so now just like before, we can try to find the gradient of this secant. So the gradient of secant again follows the general formula of the gradient of a line, so it follows this formula. And now if I want to put these values in here, the gradient of the secant PQ is just going to be the y values subtracted from each other, so f of x minus f of c over then your values x minus c. Okay, so that's the gradient of PQ. Now what we know is if these 2 points become closer and closer, then this is basically going to become pretty much the same as the gradient of the tangent. Okay, so what does that mean? As Q gets closer and closer to P, in reality it's just the x value that's getting closer and closer to C. So we can write this as a limit. We can say as the value of x gets closer and closer to the value of C, then the gradient of the secant, which is fx minus f of c over x minus c, is going to get closer and closer to the gradient of the tangent at P. Now we show the gradient of the tangent at P using f dash of c. So f dash of x means the gradient of a function. So the gradient of our function fx is equal to x squared at point C can be estimated using the gradient of the secant PQ if the value of x is getting to get closer and closer to C. So when this value of x approaches C, this is going to become pretty much the same as that. So this formula is basically what we call differentiation from first principles. So by differentiation, we mean we're just finding the gradient of a curve, and we're using the first principle, which is basically the gradient rule, to find the gradient of a point. So this formula comes in another version as well, which effectively is exactly the same thing. It's just said in a different manner. So let's look at the other version, just so you don't get confused when you see the two versions together. So again, we have fx is equal to x squared. Now, obviously, your function can be whatever it wants. It can be y is equal to x cubed. It can be y is equal to 4x to the 4 plus, I don't know, 10x cubed plus 5, right? So the reason why I'm using y is equal to x squared is just, it's easier. Okay, so let's say we have y is equal to x squared again, and we have a point P, and we have a point Q. And again, what we're trying to do is we're trying to estimate the gradient of the tangent at point P using the gradient of the second PQ. Okay, as easy as that. So what we do here is we say, fine, let's say P is located at x is equal to x, which means its y value is f of x. Okay. Now Q is a point that is some distance away from x. Okay, so its x value is some distance away from this x value of P. So let's say the distance that's away from x is h. Okay, so some distance h away from x. So that means that its x value is located at x plus h. So if you think about it, if this P was at 1 and we said that point Q, its x value is 2 centimeters away or 2 distances away, then we would say that, okay, point Q, the x value of point Q has to be 1 plus 2. Yeah? So it would be at 3. So it's exactly the same concept. So if we say P, the x value of point P is at x, then the x value of point Q is some distance away from this P value. So let's say the distance is h, and therefore Q is going to be located at x plus h. Perfect. So if the x value is at x plus h, then that means that its y value is going to be f of x plus h. Now, doing exactly the same thing. Now you want to find the gradient of the second, so you just say, okay, my formula is y2 minus y1 over x2 minus x1. And so my m value is going to be f of x plus h minus f of x over this minus that. So it's x plus h minus x. Okay? So now x cancels out with minus x, so all you have is f of x plus h minus f of x over h. Okay, so now again, just like before, the closer and closer this point Q gets to point P, then the closer these two gradients are going to become. So basically, if I bring this point Q infinitely close to the point P, then I can estimate the gradient of the tangent at point P using the gradient of the second PQ. Now what does that mean? That means that these 2 points, x plus h and x, have to get really, really close to each other. How do they get really close to each other? If this distance h approaches 0. So the closer and closer this distance between these 2 points gets to 0, then the closer and closer the gradient of the second PQ is going to estimate the gradient of the tangent, right? So we say this formula can estimate the gradient of your function at point x. You can do that. You can, if limits, so if the distance between the 2 points that you have approaches 0. So just a quick recap. This is your gradient of the second PQ. What we're saying is that this gradient is going to approach the gradient of your curve at point P if this h approaches 0. So the closer and closer this h gets to 0, as in no distance between these two, then the closer and closer this is going to be able to estimate that. And that is basically, and that is basically how we estimate